So in summary, for these different 1D problems, what we're doing is in each case we're assuming a linear change in the quantities, whether it's my displacement, temperature, chemical potential between the elements. So remember, the key things to pull out of this so far is we have a finite element node 1 and 2. My finite element is this entire thing, and over this element we define some type of material property, either a stiffness, a thermal conductivity, or a diffusion coefficient. Now we can also motivate these problems from what's called variational methods. For example, sometimes you may have a better understanding of the energy versus some type of force displacement or temperature heat flow equation. So imagine if you had an energy where for mechanics problems this would be force times displacement. If you remember, work is force times displacement. So the stored energy is 1/2 of this, and that gives you a quadratic relation. Remember, if we substitute in force equals K times delta, you get this. So if I plot that, I have a quadratic, basically saying that my spring always wants to go back to some reference state we're defining as zero displacement. So in variational methods, we basically just vary the displacement. So it's obvious that our solution, our minimum energy, is here. But in these complex problems in 2 or 3D complex loads on a boundary, you may not know where this lies. So let's just say if you don't know and we guess, you guess it's here, and now we take a variation this way. This says that my energy goes up. If I take a variation this way, my energy goes down. So basically we're looking to find this minimum energy. It's also called an extremum. We're particularly interested in the minimum. I'll later talk about whether it's a min or max and how you deal with those issues. But if we just have a quadratic like this, we only have one extremum, and it's a minimum, and this one is stable. Anytime you go this way or this way, it always increases. So that's a stable solution. One thing to think about, and we'll talk more about this in class, is what if you have a maximum? Can you get a stable solution? So when I talk about varying my energy, I vary my energy, I want it to be equal to 0. That just means that whenever my slope is 0, the energy is 0. So if I take a variation in this, I'm just taking the derivative. This is my parameter that I can vary, x, or delta squared. So if I take a derivative, I just get kx equals 0. We know that k should be greater than 0, so my solution is x equals 0. So that should be obvious from here, right? What if a force is present? So in this case, we're defining the energy as the internal energy minus this potential energy. Alright? You go through the same process, take a variation, you have kx, you also have minus f, so I'm just taking a derivative with respect to x on both of these terms, set that equal to 0, we get what we started with earlier, force equals kx. And you can find the minimum wherever finite force over k is.